Hello, in this video we will talk about electrochemical cells and cell diagrams, which is our starting point for the electrochemistry chapter. Before we do that, we should talk about what the heck electricity is. Alright, this is physics here. So electric charge is some sort of separated positive and negative charges, and maybe separation is nearby, like you have two things next to each other. Maybe your charge separation is one part is in the electrical factory and the other part is the ground next to you. I don't know, something like that. So there's some separated charges, and the SI unit of charge is the coulomb with a capital C. Now, your charges can have different, strengths in a way, that there's some potential here for your potential energy, or the force of the separated charges, and that's in volts. You've probably heard the word volt before. And this is a really common thing, like how strong is the charge here? If you combine charge, how much separation of positive and negative charges you have, with volts, the potential energy of that separation, you get energy, electrical energy, and that's in joules. And now when electrons move between these separated positive and negative charges, that's called electrical current. And so current is the amount of charge that's transferred per time, and the SI unit of current is amps or amperes. And so an ampere is the flow of 1 coulomb of charge per second. All right. So an analogy here is imagine your electrons or balls rolling down a hill. The height of that hill is the voltage, the potential energy there. A higher hill as they move with more force, in air quotes. And then how many electrons are rolling down the hill per time is the current. These are very pertinent in the world. So your power outlets in the United States of America are about 115 to 120 volts, and that's potential energy. It's alternating current, so there's some frequency associated with that, and that's in hertz. And now if you go to, say, the rest of the world, pretty much, your electrical potential is almost double, is like 220 or 240 volts. And so when you say travel to London and plug in your electric toothbrush and it can't handle 220 volts, you need to buy a new one. True story. Okay, so that's electrical things in a nutshell. And now we'll start electrochemistry by talking about batteries, basically. Galvanic cells are batteries. They make electricity through a spontaneous chemical reaction. So, for example, say we have zinc and copper. If you look at this reaction, the standard state Gibbs free energy, delta G, is negative, which means this is a spontaneous reaction. And it's a redox reaction. It's balanced at the moment, which is good. And so electrons go from the zinc, which is oxidized, to the copper, which is reduced. And if you put them in one pot, this reaction will happen very well. Zinc metal, copper ions, ta-da, you'll get zinc ions and copper metal. But that's not so useful in terms of real-world applications. And so what we do to make a galvanic cell is we separate the half reactions physically. So your oxidation half reactions over here. As the electrons go to the species that's reduced, you have it go through a wire. And then, so you don't build up negative charge on one side, you have to put some negative ions back the other way so that you continually move ions and electrons around, so you have an overall the same charge as you started with, overall neutral here. All right, so what does this look like? This is a complicated slide. Let's work through it. I'll start here. So we have our half reactions. Zinc solid goes to zinc 2+, and this is oxidized. It releases electrons. And so you have a hunk of zinc metal sitting here, and this is trying to show the individual atoms. And then, well, what'll happen is the zinc will turn into an ion, it's oxidized, and then that ion floats away in solution. And now the electrons from that oxidation go up through the metal. Because it's a metal, it can conduct electricity, which means it moves electrons. Electricity is simply the movement of electrons down a wire. All right. So then on the other side over here, we have copper. Copper's reduced, so it goes from copper ions to copper solid. So if you put a piece of copper metal in a solution of copper ions, the copper ions will take these electrons and turn into copper metal and kind of add on to the metal. And so these electrons come from the zinc. So now here's our cell, this whole thing. And so you have your zinc piece of metal sitting in your zinc solution, and that sends the electrons through this wire and to the copper where it's used for the reduction. Now, electrons moving through a wire is electricity, and so you can use this to do things like light a light bulb. In reality, this simple type of battery can't light a light bulb or even an LED, but it can make a clock tick. So there is electrons moving here. And then the ions have to move the other way. So you move negative ions into the zinc solution. You might move some positive ions into the copper-containing solution. And you want to have some sort of plugs here, so you don't just like physically mix all this stuff together. You're trying to move ions, but not like blend all your solutions together. Now, some other words here is this is called the anode. And an anode is where oxidation happens. The other thing over here is called the cathode, which is where the reduction happens. And now, thinking about batteries, for the oxidation, when you're discharging the battery, so i.e. using it, this is where the electrons come from. Wherever electrons come from, we denote as negative, because electrons are negative. And then wherever electrons go to, we denote as positive. And so on your batteries, the positive end is where the reduction is taking place at the cathode. The negative end is where the electrons are coming from, the oxidation, at the anode. Now, how are you going to remember that? Here's your mnemonic: red cat and ox. I have no idea how you would think this means, but like maybe a red cat says hi to an ox? It could work. And so reduction happens at the cathode, oxidation happens at the anode. Now, if you're charging a battery, the signs change from where they were when you're discharging a battery, like positive and negative, but reduction still happens at the cathode and oxidation still happens at the anode. Let's zoom in on this cell, the electrochemical cell. Another word for anode and cathode are electrodes, pieces of metal where the electrons go into or come from. All right. And then this is the half cell, when you have your physically separated cells like that. 1/2 cell is 1/2 reaction for your overall redox reaction. So back to this example cell, I'm going to introduce something here called a cell diagram. And this is just a shorthand way to describe what the heck's going on. And so assuming you have 1 molar of everything, because these diagrams are intended for standard states, we write it like this. So let me unpack this for you. So the anode's on the left, cathode's on the right, oxidation, reduction. That's usually how we write it. You've noticed through all my slides, I put the oxidation first, then the reduction. So that's what we're doing here. These lines denote a phase boundary, because solid zinc is different than aqueous zinc, and aqueous copper is different than metallic copper. This double line in the middle shows the salt bridge, and it's showing that you're physically separating these two half reactions. And you can put the counter ions in, you don't have to, doesn't really matter. What matters is the zinc 2+ and the copper 2+. Now, the directionality here, like why do we put the zinc first and the zinc sulfate second, is because the reaction goes this way, right? If you look up above, zinc is a reactant, zinc sulfate is a product, or just zinc 2+ is a product, so reactants to products, left to right. That makes sense. And then copper ion is a reactant, copper solid is a product. So that's why we put them in this order. Hopefully that's a little easier to remember. Okay. So now another example. Let's take this reaction, this redox reaction, and build the electrochemical cell diagram out of it, and we'll show what that looks like in reality too when you make it. So looking at this, the zinc is oxidized, just like it was in the previous example, and now hydrogen is reduced. Hydrogen ions from an acidic solution are reduced, and this is a balanced reaction, so that's good. It needs to be balanced, right? Now let's build this cell. All right, so we can put the zinc metal in the zinc solution. All right. We have hydrogen ions. Okay, that's easy. Hydrogen gas, that's going to bubble out of the solution and not actually work in terms of, doing the redox, because you don't have a piece of metal to serve as your electrode. So when we actually do this in reality, you have to add some metal that's not going to react with this redox system to provide a pathway for electrons to reach this solution. It's the electrode, but it's not part of the reaction. Platinum, gold, and carbon work pretty well for this purpose, and we use them as electrodes frequently. All right, so here's the reaction still. So what this looks like physically, all right, the left side is pretty similar to what we were just looking at. It's still a salt bridge, still a wire, okay. And now instead of this coming into a hunk of metal, because hydrogen gas is not a metal, you have an electrode here that sits at your interface between hydrogen gas and the hydrogen plus aqueous solution, and that allows for the electrons to come in. So the cell diagram of this is the zinc part, the oxidation reaction, And that starts with the solid and goes to the ion, just like before. And then there's the salt bridge in the middle. And then you have left to right HCl plus goes to H2 gas. And then we throw in the platinum at the end because it has to be there. And, which metal you use, you want to specify that. All right, and last thing I have to say in this video is that we have different words for this electrical potential between anode and cathode. We'll often call it the cell voltage, or sometimes the electromotive force, EMF, or the cell potential. Often voltage and potential are used interchangeably because voltage is just electrical potential energy, so we often switch those up, or you can use EMF. And that's all I have for this video. Thanks for watching.